Chloromethane reacts with sodium hydroxide to give methanol. Methanol is a polar molecule. Explain the above observations using your chemical knowledge. So I've sort of captured that now in chemical formulas, which we're able to understand. So here's the Lewis structure of methane. At 16 grams per mole, it has a melting point of negative 183 and a boiling point of negative 162. So again, I'm bringing this stuff up because part of the reason why you're studying organic chemistry, aside from it being a requirement for your major, is to understand the properties of these substances. And we use substances in everyday life. That's what makes our modern civilization possible, is this chemistry that's been developed over the years. So if we take methane and we treat it with chlorine gas and light or heat, it affects a radical substitution. So substitution is the substitution of the hydrogen for the chlorine. The radical is telling you the mechanism by which this happens. So this arrow in red here, this FGT, that stands for functional group transformation. And really, this is what is going to concern us for the rest of Organic 1 and Organic 2, our reactions. So we're taking an alkane and we're making a haloalkane through a functional group transformation that occurs through this mechanism. Chlorine has the molecular weight of 50.5 grams per mole. Notice the melting point changes significantly, as does the boiling point. So what you're trying to develop now is an intuition or an understanding about how a nonpolar molecule, when it becomes polar, these properties change. So why does this element affect these properties? So we've talked about some of that earlier in this semester. If we take this molecule, chloromethane, and we treat it with sodium hydroxide, need to put my formal charge in here, so that's the hydroxide is negative. This is going to do a substitution of the chlorine for the hydroxide to give methanol. So the molecular weight then decreases to 32 grams per mole. The melting point stays the same in this case, but the boiling point changes significantly. Now what we're also concerned with is this here. So notice we substituted the chlorine for the hydroxide to get that, and then we have the byproduct here, sodium chloride. So the reason I'm bringing that up is because it's important in understanding this process here. This is a different mechanism by which this substitution occurs. This is called nucleophilic substitution. Radical substitution occurs through a single electron moving. Nucleophilic substitution occurs through two electrons moving. So we call this a radical, and we call this polar. Polar meaning two electrons. So just to throw in some spectral data so we don't forget. Again, the spectral data is things we talked about in terms of proton and carbon. So the carbon of methane occurs at 0 parts per million. The hydrogens occur at 0.23 parts per million. On the scale for carbon and proton, you can actually go negative depending on how much those elements are shielded in the environment they're in. So let's see how that changes when we substitute the H for the Cl in chloromethane. The carbon then shifts to 25 ppm. The hydrogens then shift to 3.08 ppm. And again, the reason I'm telling you or reviewing this is because we're trying to understand the substitution of H for chlorine how we can then observe that using instrumentation. So notice the halogen shifts it quite a bit in terms of the carbon and the proton. So when we do substitution of Cl for OH, the carbon now shifts to 50.2 parts per million. These hydrogens occur at 3.48. So notice, again, to recap, the hydrogen scale is from 0 to 10, so it's much more compressed. So you don't see like huge shift differences when you do these functional group transformations. Whereas in the carbon NMR, because it's 0 to 220, you get quite a bit of gap between the functional groups. The other important thing is, so in the OH, for the IR, we see that broad shift at 3,500 reciprocal centimeters. Again, this stuff is important because how do we figure out that this substitution actually occurred? And we use this spectroscopic data. So let's move into where I have explain here. These two reactions that are drawn are stated in words here. So I've actually just drawn them out. So if we take sodium chloride and we react that with methane, this chlorine anion, chloride, Cl minus, will not, I'm going to put the not in here using a red X. This chloride will not substitute that hydrogen to give chloromethane. And notice the byproducts that I've drawn. Sodium, H minus. Sodium hydroxide plus methane will also not react to form methanol. And notice that these are the same. These co-products end up the same because what's in common? The sodium cation and then this H here of methane. So we want to understand why these reactions do not occur, but this reaction up here does occur. So we know that chloromethane is a polar molecule. So we have Cl bearing 3 lone pairs. So we can say that's delta minus, and then the carbon's delta plus. So chlorine here, delta minus, because we have 3 lone pairs. Carbon's delta plus, because we have a polar covalent bond that's polarized. So now look at the difference between this starting material, which does a substitution, and these which do not. So this is a neutral, nonpolar molecule, right? We're taking these ionic compounds with something neutral, nothing happens. So we want to understand why nothing happens. And in understanding that, if you look here at the nucleophilic substitution of chloromethane for methanol, this right here is important. See that Cl minus? Remember when we were talking about acid-base chemistry, and we said that HCl is a very strong acid. So an acid donates its proton. So the conjugate base of HCl is Cl minus. So Cl minus is very stable, right? So if we compare that to this here, H minus, otherwise known as hydride, hydride is the conjugate base of hydrogen H2, right? So if we do an acid-base reaction of H2, where we're donating a hydrogen atom, H minus is the conjugate base. So for substitution reactions, what we are doing is evaluating the starting material if there is what we're going to use the term a good leaving group. A leaving group can be defined as something that is a conjugate base, because that's what it ends up being here in the coproduct. So if you look at this compared to that, we see that this is not a good leaving group. Any questions on this slide so far? So let me skip, move back. So before we get too far into it, I want to talk about halide classification, because that's going to be important for determining the type of substitution that can occur. So there are two types of polar substitution. The first one we're going to really spend some time on is called SN2. The second one is called SN1. And so what do these terms mean? So S means substitution in both cases. N means nucleophilic, and then this number here, 2 versus 1. 2 means bimolecular, 1 means unimolecular, and that deals with the rate equation. So let me write that down. S equals substitution. N equals nucleophilic. So again, that's what I mean by polar, or 2 electrons moving. 2 equals bimolecular. 1 equals unimolecular. And again, that has to deal with the rate equation. So bimolecular means that you have to have 2 species colliding for the reaction to occur at the rate limiting step. Unimolecular means only 1 species is present to determine the rate limiting step. So I want to talk about halogen classification in relation to how do you know this versus this is happening. So in the last part of this semester, which we're in now, your book focuses on substitution reactions, which I've shown you there's 2 of them, SN2 and SN1. So those are grouped together, substitution. Then there's another group called elimination, E2 and E1. So what we want to make sense of, when you are given a substrate, how do you know if substitution is happening versus elimination is happening? The first decision point that you make is you classify the halide that you're starting with. So let's draw those out. So we have methyl, that's just simply CH3X. And again, X is a halogen. We have primary. So say, for example, the primary of ethane. Then we have allylic primary. So I'm just using this term here, allylic, but it's still under the primary. What does that look like? allylic is this position. It is the sp3 hybridized carbon that's directly bonded to the alkene. So that's allylic. We have another primary called benzylic. So benzylic is the sp3 hybridized carbon directly bonded to the benzene ring. So this is the benzylic position. This is the allylic. Notice they're still both primary. So we have secondary. So for this, I'm just going to start using the bond line. So if we consider propane, that would be a secondary halide. Then tertiary. That would be tertiary. And now I want to talk about another primary case, but this one has a special name. I'm going to put it way over here. It's called neopental. So neopental is primary, but it's a special case because of the following. So the X group, the halogens, bonded to this primary carbon, and that primary carbon is immediately bonded to a tertiary carbon. So let me just write that in red so we know what that means. So here's primary, and then there's the tertiary. So that's what we define as neopental. You have the X group bonded to primary, and that primary is bonded to tertiary. And the reason that matters is because when we talk about the polar reaction substitution, we need to think about things in three-dimensional space. So when we're talking about a tertiary carbon with three groups on it, that carbon is very hindered. And the mechanisms that we're going to see have to have a certain trajectory. So if you think about in football, when the quarterback is throwing the football to a receiver, the sterics matter. If the quarterback has a lot of defenders around him, he can't get the football through them. Alternatively, if the receiver has a lot of defenders around him, he can't accept the football being electrons in this case. Any questions on the classification of the halogens so far? So right now I'm just straight up telling you some facts. And as we learn this mechanism, we're going to see how those facts apply. So I'm gonna switch the color over here. So maybe I can do this. I'm going to use the highlighter. So in green, I'm going to highlight SN2. So methyl, primary, and secondary. So if you look at a substrate and you classify it methyl, primary, secondary, those will undergo SN2 reactions. So maybe in red, the neopental the tertiary, and now this is the sticking point here, this overlap, those undergo SN1. So if you've sort of read already some of the book, a substitution is a substitution. So regardless of which one of these types you're starting with and how the mechanism proceeds, it's still substitution. What matters, though, is how that substitution occurs based on how you classify these things. Because if you did that, that prompt I gave you about the C6 hydrocarbon, if you do chlorinations of that, how many do you get? And if you consider stereochemistry, it's a lot more. The issue in studying these is there are stereochemical issues we have to consider. And so the bimolecular versus the unimolecular has consequences on the stereochemical outcome of the reaction. Any questions so far? So let me ask you a question. Very broad. I know you might not understand the intent, but what do all these, see these carbon X bonds? Other than the X halogen group, what do all the carbons have in common? So they're bonded to carbon and hydrogen. That's true. Think a little bit about other things you've learned so far in this course about classifying things. So in one sense, I showed you what they were classified as, but the carbons themselves, what's another way you could classify the carbon atoms? Maybe I'll give you a hint. There are certain types of carbons I have not drawn up here yet. What other types of carbons have I not drawn? And again, what I'm aiming to help you guys understand is when you are given a substrate or a starting material and you want to understand which type of mechanism it goes through, you're classifying the type of halogen, but you're also looking at the carbon begins with an H. So hybridization. So what is the hybridization of all of these carbons that's shown? So the carbon hybridization of all of these is sp3. So that's important for you to accept as fact. So let me write that down. The carbon must be sp3. So the following substrates that I'm drawing do not react by substitution. So again, this is sp2, sp2, sp. Now I know it's sort of subtle, but it's important. So here, notice the X group is bonded to an sp3 hybridized carbon. X is bonded to sp3. Now here it's bonded directly to sp2, sp2, sp. That's important. So just be aware of that. So again, for substitution and later on in the semester elimination, we're only dealing with sp3 hybridized carbon. To this and sort of show you on this scale, which we've seen before, what I mean. So again, in that example, I said HCl is a strong acid, right? We go over, it has a -7 pKa, that's how we know it's strong quantitatively. And then we said that Cl- is the conjugate base. So let me just write those things down, what we're comparing. CH3Cl. This is delta minus, this is delta plus. We said that reacts. CH3H. There's no real polarity difference between H and carbon, right? So we can't assign any sort of dipole moment. So if we're looking at the conjugate base of this, that comes from H2, which is way down here. So this is a pretty weak acid. We go over, it has a pK of 35. Now its conjugate base is H-. So we see here that weakest base results from the strongest acid. So as we go down this column, we're increasing the base strength. So strong base, we see that here. So we're going to transition from using sort of base to different terms when we talk about the SN2 or polar reaction. So this conjugate base here, which we see Cl- is very stabilized. It's able to handle the negative charge that it's bearing. Hydride, on the other hand, is not. It's very reactive. So we want to make an association with leaving group and conjugate base strength. So conceptually speaking, to do these type of substitution reactions, you have to have a group that when it leaves the leaving group, it's stabilized. And so really what we're talking about for the most part are things that have are in a sense their conjugate bases bear a negative charge that's stabilized. So this thing here, we'll talk about that leaving group, chloride, bromide, iodide. So really we're going to talk a lot about halogens. Halogens being in the molecule, which we saw from chapter 10, we get them in there through a radical substitution of tertiary versus secondary versus primary. That's how we know specifically where in the molecule we can do a radical substitution. Now in chapter 7, we want to do a functional group transformation where we substitute that halogen for something else. And the halogen becomes the leaving group. We're substituting it with a thing called a nucleophile now and doing a functional group transformation. So any questions so far? So let me move on to the next slide, so I'll come back to this slide, but it's important because it really puts everything together about substitution reactions. So AZT, when you look at this molecule, it goes through a synthetic route to form this molecule, and then just through observations we'll talk about what is changing, what are the issues, and then what do we have to consider. So we're gonna bring in some new terms for that as well. Please look at your homework, start doing those, as well as your professional development activities, which are due November 23rd at the end of the semester. But if you have questions or anything, shoot me an email. I'll probably respond with a video, or if you want to meet, I'll respond with a Teams invite. But other than that, we'll go ahead and stop for today. Let me just go here and talk about our decision points of employing an alkyl halide, whatever type, in a substitution reaction. So let's consider the reaction we saw on the first slide. There's chloromethane. By now you should be able to assign delta minus, delta plus. We were reacting that with sodium hydroxide. It does a substitution. So again, I'm going to keep hammering these words. Cl is substituted for OH. So we get methanol. And so those are the things that are participating in the reaction. Now what I'm going to do is I'm going to generalize. When we were in chapter 3, I believe, on acid-base chemistry, acid-base reactions are a specific subset of reactions. Now what we are doing in learning reactions, we are zooming out from the microscopic view, and we're taking a broad view of the reaction space. So we're going to use different terms in that sense. So we're going to use the terms from the Lewis definition. So in these things that are shown, I'm going to use these different terms, and that's what we're going to use from now on when we talk about reactions that are not specifically acid-base ones. So our substrate here bearing the halogen, this is called an electrophile. Electrophile. It's called that because we have a carbon bearing a positive charge, and we have this thing bearing a negative charge. And I keep forgetting this negative charge here, which I will put in. So the electrophile reacts with a species which is called a nucleophile. So, and then we can say this is product. Sort of know that. Then we have this co-product. So maybe I'll ask you a question without showing the arrow pushing formalism yet. I've used electrophile and nucleophile. So below those terms, then I wrote this Lewis here. Looking at these two things, if you had to classify each of them as acid or base in the Lewis sense, which would be the Lewis acid and which would be the Lewis base? So the electrophile would be the Lewis acid, that's correct. This would be the Lewis base, the nucleophile. So what again was the definition of a Lewis base? So in the chat, what's the definition of a Lewis base? So yeah, Blakely, check out Ian and Mac's responses. A Lewis base is an electron pair donor. So keep that in mind. We're talking about polar reactions now. A Lewis base donates a pair of electrons. A Lewis acid accepts that pair of electrons. So the reactions we're learning, there is always a nucleophile electrophile pair. So how do we show that with the arrow pushing formalism? Just as we saw in a typical acid-base reaction, the arrow starts at the base and it points towards the electrophile or the positive species. So if we are to show this substitution occurring, the arrow starts at one of the lone pairs of the hydroxide, so see how that's negative, and it's going to attack the partial positive of the electrophile. So negative is attracted to positive. We know from our normal Lewis dot structures, carbon has to have 4 substituents or ligands. Oxygen has 2. So if we're forming a bond between this oxygen and that carbon, we have to then remove this bond. This bond has to cleave. If the oxygen is supplying 2 electrons, these 2 electrons then leave with the chloride. So notice that double-headed arrow. That means 2 electrons are moving. And why does the arrow point this way? Why do these 2 electrons in this bond go to chlorine? Because we already assigned this delta minus. See how we have 1, 2, 3? This is supplying the 4th. So in here we have 1, 2, 3, 4. That's how the chlorine becomes chloride and negative. So this thing here is called the leaving group. It go bye-bye. So I'm just going to abbreviate that LG for leaving group. So the leaving group stability is determined by pKa of the conjugate acid, Cl minus the conjugate acid is HCl. So now we sort of have to think in the reverse fashion. There's your leaving group. The chloride, again, is the spectator. It balances out the charge. The leaving group is Cl minus. We know Cl minus is a weak conjugate base because it has a strong conjugate acid. So the substitution reactions, for the leaving group to be a good leaving group, it has to have a very stabilized conjugate base of its starting acid. Are we clear on that? So what I want to talk about a little bit more in depth is this arrow here, where the nucleophile is supplying the electrons to attack. So what we've sort of shown is maybe a Polaroid picture of the start and the end. So just two snapshots in time. But if we want to consider all the time in between, that would be our reaction coordinate diagram. And so if we think about the timing of this, again, if the nucleophile is the quarterback is holding the football, which is the two electrons. The arrow represents the trajectory of how the football is thrown. The electrons can only be received by the electrophile, which is the receiver. So this trajectory has to happen in a certain way. That's what I want to talk about now, how it relates to hybridization and why sp2 and sp hybridized carbons cannot undergo this process. So what I'm going to do here is sort of draw this out with a little bit more detail. So I haven't drawn the carbon or the hydrogen atoms in yet, but let me ask you a question. What type of bond is this right here? So you should be able to look at a bond and classify the bond type. It's a single bond. What's another term for that? So it's a sigma bond. Remember when you have two elements coming together to form a bond. So you have 1, 2. You have this thing which is drawn as called a bonding orbital, right? But if two atoms are coming together to form one bond, you have to also form something else. What else do you form? You have a bonding orbital, and then what else? So this is sort of like the law of orbital conservation. So Cole says molecular orbital. So I'm looking for a little bit more clarification on that. So if this is a bonding molecular orbital, you're forming another thing. I don't want to, I don't know another word for it, so if I say it, I give you the answer. So if this is bonding, you form another thing which is, so the anti-bonding is the term we're looking for, the anti-bonding molecular orbital. So notice the directionality of this bonding orbital. The electron density is polarized between carbon and chlorine, so that's what this negative means. More of it is sort of towards the chlorine. If the orbital is pointed this way, where do you think the anti-bonding orbital is pointed? The anti-bonding orbital is empty at this point. There's no electrons in it. Which directionality do you think it has? So when I drew this arrow up here, the nucleophile attacking the electrophile, I sort of drew it just sort of half-assed willy-nilly. But now what we're really getting at is what is the true trajectory of those electrons to attack that carbon. So if you have this bonding orbital between these two in this direction, the anti-bonding orbital faces this way. And so I'm going to draw that in the following fashion. So that's what the anti-bonding orbital looks like. It has a giant sort of lobe right behind the carbon, and then a smaller little lobe that overlaps with the bonding orbital. So we said that the electron density between the bonding orbital is primarily on chlorine due to the electronegativity. The anti-bonding orbital is larger in size behind the carbon for the opposite reason, because the carbon's sharing less of the bonding electron density. So let me put these terms in. We have, there's our sigma bond. We'll say sigma C, Cl. And then this is our antibond. Again, the sigma bond has the electrons, the antibonding sigma star does not. So now that you see that directionality, I'm going to go ahead and put in the hydrogen atoms for the sp3 hybridized carbon. So here's your sp3 hybridized carbon, hydrogen, hydrogen, hydrogen. These bonds are in the plane. This is coming towards you. This is going away. So now the nucleophile, which is supplying the electrons, the trajectory of those electrons is directly opposite the existing bonding orbital, and the electrons are going right into the anti-bonding orbital. So this trajectory, and I know this is getting a little bit busy, but the angle between the nucleophile, the carbon, and the electrophile leaving group that angle is 180 degrees based on the orientation of the bonding to the anti-bonding orbital. So once those electrons go in, these electrons are going to leave. But again, we're slowing down our thought process so that we're on like the femtosecond scale here. So instead of seeing two Polaroids of the start and end, we're actually seeing a movie as this occurs. So as this transpires, we go through something which is called the transition state. And remember we said the transition state was the top. We're going uphill. It's the top of the energy curve for the reaction coordinate. So the transition state is very fleeting in existence. During that time, the carbon actually changes hybridization to sp2 hybridized. And so why is that? I'm going to draw in the hydrogen atoms. The reason that is because you have to have partial bonding between this oxygen and this carbon, so partial bonding. And you also have to have partial bonding here because this is forming and that's breaking. And again, we're slowing down the movie so that we can see this and we're not just seeing discrete endpoints. So how do we represent that? Here is your p orbital. Again, has lobes in front and back. OH, you're partially forming that bond. You're partially breaking this bond. So you have, this is delta minus, delta plus, delta minus. This is sort of losing its negative charge, and this is gaining more negative charge. So you're forming this one, you're breaking that one. So to accommodate this, the hybridization changes to sp2. And so now that actually makes sense in terms of the 180-degree relationship between those two. And then as the reaction, as time proceeds, you fully form this, you fully break that. And now you're back to your sp3 hybridized. So one thing I want to point out, maybe two things, it may not be completely obvious to you, or because it's sort of subtle, but see these hydrogens here? They're sort of on the if you had to classify these three, they're sort of on the left side of this carbon. But notice as the reaction takes place, sort of how they pivot in a sense. They're on the left side. Here they're sort of in a central plane. This bond forms, this bond breaks. Now look at them. They're on the right side now, right? So they started on the left. They're in a central plane. Now they end up on the right. That's called inversion. And for this specific case, it's sort of hard to understand because you have three of them. They're all hydrogen. They're the same. But think about if you were starting with a secondary chloride, and the secondary position was a stereogenic carbon, that carbon would invert. There would be inversion, and you would actually see it in terms of how the nucleophile comes in and the leaving group leaves. So I'm just going to throw that out there now, inversion. And we'll come back to it when we get into a case where it's actually sort of noticeable and we're not dealing with just with hydrogens. Now let me ask you a question regarding when I said for this reaction, we have hydroxide attacking this. So there's one, there's two. So that's our SN2. It's bimolecular. So in the rate limiting step, this and this are both in the kinetic equation. The nucleophile has to attack this antibonding orbital. We said that when this carbon is tertiary, it does not undergo SN2, but rather it undergoes SN1. Looking at this carbon, why do you think that is? When the carbon's tertiary, why does SN2 not occur anymore? So think about this mechanism when we said this trajectory. The nucleophile has to attack the antibonding orbital. So that is existing in this space between these groups. So this is specifically methyl, but if you were to substitute this for carbon, carbon, and carbon, now you're increasing the steric bulk, the hindrance around that carbon. So this antibonding sigma orbital becomes less accessible as you increase the substitution around that carbon. So the reason that methyl primary and secondary can react through SN2 is because the nucleophile can still see this antibonding orbital. When it gets to tertiary and neopental, that's no longer the case and it reacts unimolecularly. So at this point in an SN2, we sort of see the trajectory that's needed. We've talked about inversion, and in the last few minutes here, I just want to plot this according to a reaction coordinate. So on the the y-axis, we have our energy. Then the y-axis is our time. And so the energy that we're talking about, it's all relative, so we're not using absolute terms here. So we're starting off at some energy of our reactants. So as this reaction proceeds, the transition state is higher in energy, so we have to go up. The reason it's higher in energy is because it's a reactive species, and those things necessarily by definition have to be higher in energy. So from the reactants, we're proceeding uphill. Maybe I'll just draw this in a different color. We're going up. So we go up in energy to the transition state. Remember, we said the transition state is fleeting, so once you get to the top, you're either rolling back towards the reactants or you're rolling forward towards the products. So if the reaction is evolving heat, then we're going downhill to our products. So in this sense, overall we're evolving heat. Now if we're using the free energy terms, so delta G, that's the Gibbs free energy, we would say this delta G here is the change in energy to the transition state. And then overall for the reaction itself, delta G, we use that little degree or naught symbol. So those are two terms you'll have to know: the free energy change to the transition state, and then the free energy change to the reaction. So we're about out of time for this discussion today. We'll continue on Wednesday talking about substitution. We'll finish up SN2. We'll transition into SN1, that's the unimolecular. And what I also want to do is talk about